By the end of this video, you will be able to produce the 5 notes of a major pentatonic scale. In the video Invitation to Music Theory, we describe part of the process of generating harmonics on a vibrating string, and in the video Harmonics on a Vibrating String, we describe this process more fully. In this video, we will describe in detail the second part of the motivational video, the generation of the notes of the C major pentatonic scale, so that you can carry it out in practice. For this, we will use the simple instrument shown in the figure. The procedure used for this purpose will be the following. We will begin by pressing both strings in unison to verify that it is impossible to differentiate between their sounds, and we will register this frequency as the first of our search. Then we will adjust the length of the second string to vary its frequency, and pluck both strings in unison. Each time this action produces a pleasant sound, we will enter this new frequency in the table. According to the videos reviewed, the frequency of the fundamental motive vibration of a string is given by the expression shown in the upper right. The strings of the instrument are identical and are tensioned to produce the same fundamental frequency of 260.74 Hz shown to their right. Let's start the experiment by simultaneously plucking both strings. Since the vibration frequencies of both strings are identical and have been struck simultaneously, it is impossible to distinguish between the two sounds. Let us note this frequency, which corresponds to the C of 260.74 Hz, indicated by C4. We will then begin to vary the frequency of the second string, adjusting it to a fraction n over d of its length, that is, according to the expression for the fundamental frequency, 1 will have. Now let's move the yellow knot to set the ratio of the lower string length to the upper string length to 2/219 of L. This setting produces a dissonant sound that is not very pleasant. We will discard it. We continue the experiment by adjusting the lower string to half the length L to produce twice the initial frequency. 1 octave interval. Although a richer sound has been obtained than in the case where the lengths are equal, it is very difficult to distinguish between the sounds of the two strings. This is a result that we had already obtained in the video experiment in which the vibration of a string was studied, so we know that this is so because this frequency, corresponding to the C of 521.48 Hz, indicated by C5, constitutes the second harmonic of the sound produced by the first string, the C of 260.74 Hz, C4. The sound of the second string constitutes only a reinforcement of this sound and that of other harmonics produced on the first string. The conclusion we come to is that sounds related by multiples constitute in essence the same sound, what in theory is known as class. We will take this as the last note in our table and concentrate on searching for sounds contained in the range of 260.74 to 521.48 Hz. That is all we need. We will not enter this octave in the table for the moment, but we note its value below the instrument to keep it in mind throughout our search. Now let's move the yellow knot to set the ratio of the lower to upper string length to 2/3. This adjustment to 2/3 of the string length produces a joint sound in which it is possible to distinguish between the sounds of both strings, and which is pleasant to the ear. We will note this in the table. Now, multiplying by the factor of 2/3 the string length corresponding to the last note in the table is equivalent to multiplying its frequency by 3/2. If the frequency resulting from this last calculation is less than 521.48 Hz, adjust the string length by multiplying by 2/3 the string length corresponding to the previous note and verify on the instrument that the result is agreeable, and if it is, enter the data of this new note in the table. If when multiplying by 3 halves the frequency of the previous note a frequency higher than 521.48 Hz is obtained, this must be reduced to the octave considered by dividing its value by 2, which we achieve by multiplying by 2 the product of the length corresponding to the previous note by 2/3, that is, by multiplying this length by 4/3. If we multiply the frequency of the last note by 3 halves, we get a frequency of 586.66 Hz, which is higher than 521.48 Hz. Therefore, we use an adjustment factor of 4/3 to the previous length, with which we obtain a length of 8/9 of it. We will use this value in the instrument. This setting to 8/9 of the length of the string produces a sound of the whole of both strings that is pleasing to the ear. We will record it in the table. If we multiply the frequency of the last note by 3 halves, we obtain a frequency of 440 Hz, which is lower than 521.48 Hz. It corresponds to the note A identified as A4. Therefore, we use the reduction factor of the length of the string of 2/3, with which we obtain a length of 16/27 of L. We will use this value in the instrument. This setting of 16/27 of L of the string produces a sound of the whole of both strings that is pleasing to the ear. We will record it in the table. If we multiply the frequency of the last note by 3 halves, we get a frequency of 660 Hz, which is higher than 521.48 Hz. Therefore, we use a factor of 4/3 to modify the length of the string, with which we obtain a length of 64/81 of L. We will use this value in the instrument. This setting of 64/81 of the string length produces a sound of the whole of both strings that is pleasing to the ear. We set it on the table. We could continue the search for notes, and we will do it in the next video, but for now we will stop this search with the incorporation of the note corresponding to the octave interval that we obtained at the beginning of the experiment. It is interesting to make a diagram in which the notes are placed evenly spaced and arranged alphabetically clockwise on the circumference of a circle, and joined by strokes in the same order in which they were generated, that is, by fifths. A regular 5-pointed star is obtained. In the theory of scales that we will see in subsequent videos, musical notes are usually arranged in increasing order of their frequencies. Let's rearrange our table following this criterion. Let's consider again the notes on the circle and join them in strokes following the order of their frequencies. We will listen to the C major pentatonic scale. We have worked laboriously to obtain the 5 notes of the major pentatonic scale, but we can now begin to see the results of our efforts. Let's extend the last table to the C note of the next octave. On it we can observe the performance of the beautiful and well-known melody, Amazing Grace. The description provides a link to our associated website where you will find a simple 2-octave pentatonic keyboard with which you can practice this melody, or produce your own melodies. Thank you for watching this video. In the next theory video we will continue the search for musical notes.